Okay, so today we're going to talk about tuning neural networks. This is a little bit out of order from the learn lessons, but in order to, I think, accommodate the next project better, I actually changed the order of the topic so you get into tuning neural networks before some of the other stuff. So today, we're going to sort of build off what we saw last time when we were building a neural network. You saw that there were a lot of different parameters that we were using. So today we'll get a little bit deeper about what those parameters mean. So today's agenda, we'll talk about all of these things related to tuning neural networks. We will also talk about these two things, convolutional layers as well as pooling layers, and how these work specifically for image classification. I also want to caveat that if you're doing an image classification project, you don't necessarily have to use these things that we're going to talk about later, because this is actually technically in the appendix, but you will get much better results if you do. So therefore, I do want to introduce it as part of curriculum. But if you are working on the image classification project and you don't want to do that, that's okay. All right, so let's get into some of the things that we're going to tune. Tweaking neural net parameters. I found this GIF. I think it is very indicative of what that process is like. It is not easy. It's hard to tell what changes you make in a neural network will lead to, how much improvement. So it's really, one, a trial and error, but two, also you do have to have much deeper understanding of different things like activation loss functions, optimizers, in order to tweak your neural network while being informed. So just know that at this stage, you don't have to have a really solid understanding of every little part of neural networks. It's more about, all right, we're testing different things and finding out how combinations of things work best together. So yeah, to start, the first thing we're going to talk about is adding nodes and layers. So as we saw last week, on Thursday with our sample neural network, we actually added multiple hidden layers into our dense neural network. So one thing that you can do is you can just add more layers. The more layers you have, the more parameters there are to adjust. And just by adding a whole new layer with X number of nodes, you increase the precision, or not precision because that is an accuracy metric, but you increase like the granularity of your decision boundaries. So for many problems, you can start with one or two hidden layers. It'll work just fine. But for more complex problems, you can gradually ramp up the number of hidden layers until your model starts to overfit. Very complex tasks like image classification without convolutional layers will need dozens of layers. So as I mentioned just now, with image classification, we will talk about convolutional layers at the end of today. But if you're not going to use convolutional layers, it's going to be hard to get a good result just using the dense layers that we were playing around with last Thursday. Aside from the number of hidden layers, you can also adjust the number of neurons per layer. So again, the number of neurons for your input and output layers is going to be dependent on your data and the task. So as we saw for our very first neural network layer, we had to tell it the input dimension. So we had to tell it how many columns our input data had. And then for your output layers, again, it depends on what you're trying to predict. If it's a binary classification, it'll just be one node at the very end. If it's multi-class, you actually do an output dimension of 5, if it's 5 classes. So yeah, input dimensions determined by your number of columns. And yeah, for your output layer, it's just one node with sigmoid. But for hidden layers, it really doesn't matter how many nodes you have. Of course, the more nodes you have, the more intricate your predictions will get. But yeah, for hidden layers, a common practice is to create a funnel, and you get fewer and fewer neurons per layer. So let's say you start with your very first layer with 128 nodes. Your next hidden layer usually gets smaller. So you could go 128 down to 64, down to like 32. But the exact number, increasing the number of nodes by 1 won't change your result by too much. So yeah, in general, you get more bang for your buck by adding on more layers and adding more neurons. So when will you think about adding layers and or neurons? Probably layers, honestly. If you find that your model is not learning anything, if you find that your loss function is still high, your accuracy or whatever metric you're using isn't improving, you might want to consider adding more layers. When you want to think of subtracting layers is if your model starts to overfit. Any questions at this point? Cool. All right, so the next thing we'll see is activation functions. And we're actually going to come back to all of these at the end because we're going to build another neural network at the end of today. So activation functions. I will say activation functions is probably the most mathy part of neural networks. Activation function is the thing that gets differentiated to do backpropagation. So really understanding, when to use what activation function and how that will affect your learning, that's honestly very, very advanced. So I wouldn't worry about it too much for now. Just know that several things that you have to consider with activation functions. One, differentiability, because again, as I mentioned, the derivative of your activation function is used in the backpropagation process. So we'll talk about a couple of things about what happens, some implications of differentiability of your activation function being important. So for your hidden layers, I'll talk about hidden layers first. I've linked some articles that walk through in a little bit more depth what each activation function does. As I mentioned with the example of using a logistic regression to act as like a single perceptron, we talked about sigmoid being the activation function. Interestingly, sigmoids are actually not used very often within a hidden layer of a neural net because it has a small maximum derivative value, therefore only propagates a small amount of error each time, leading to slow learning. Now, if this doesn't make sense to you, in short, it just means that when you take the derivative of a sigmoid function, because of the nature of what its derivative looks like, your learning rate will be very, very slow. And this learning rate is the learning rate that is a result of the activation function rather than the actual learning rate. But yeah, because of the small derivative value, it learns slowly. So you would find that if you have hidden layer activation functions being sigmoids, your neural network will only get to like the same amount of accuracy with more epochs, for example. This small derivative slow learning issue is known as a vanishing gradient problem. So if you ever come across this phrase, that's what it means. Another activation function you have is tan H, which is actually very, very similar to a sigmoid function, but it also has a vanishing gradient issue, but it's not as bad. So let's say you're using ReLU and then that is overfitting. Maybe you want to downgrade to a tan H. But as I just mentioned, ReLU generally works well because its gradient's always 1 and the input is positive. ReLU function actually looks like this, a straight line. So you don't have this vanishing gradient issue. And then also, if you see at the first half of a ReLU function, it's all at 0. Anything that is a negative input before getting passed through your activation function actually becomes 0. So it makes your network a little bit lighter. By lighter, it just means that less computation needs to go on. Any questions at this point?
Yeah, I have a question about leaky ReLU. So it seems pretty similar to ReLU, except that it starts a little less than 0.
That's right. Yeah. So basically, ReLU having negative inputs all going to 0 may or may not be a good thing, because as I think I wrote it here, right? Negative inputs will all go to 0 and it doesn't update any weights and biases. So therefore, I mean, pros and cons, right? You're making your network work lighter because it doesn't have to update these nodes, but then you lose out because it isn't updating the nodes. So leaky ReLU just kind of accounts for that. Leaky ReLU is, I think, well, it was developed after ReLU. And I would say that if you're facing things like underfitting, leaky ReLU would be something you consider over ReLU.
All right, thanks.
You're welcome. When it comes to these, I know it's hard to think about, all right, with my specific problem, which one to use. I would say most basic neural networks, using ReLU is fine, maybe TAN-H. Those are the two that people usually test for. In next week's study group, I'll actually walk through a way that you can do grid search on a neural network. And then that will just make the process a lot more automated, so you don't have to keep running a bunch of neural networks. Now, just now we talked about activation functions, but only for hidden layers. Now, activation functions is a little bit easier to think about for your output layers. So actually, let me pull up that Colab notebook that we had so we can see what our activation function looked like. Let's see, hopefully everything is still there. There was our neural network. Okay, so these were our two hidden layers. We use ReLU over here. And then for our output layer here, and let me just zoom in once more. For our output layer here, we used a sigmoid. And in this case, we use a sigmoid because we were doing a binary classification problem. So when thinking about your activation function for your output layer, it does matter what your problem is. So I've listed a few common examples here. For binary classification functions, you want to use sigmoid to coerce your values between 0 and 1. Same concept as for a logistic regression. If you have a multi-class problem, usually people use softmax, and softmax is just another activation function. Because the product of softmax, it produces a non-negative vector that sums up to 1. And what that means is if I have 5 different classes, the output's going to be 5 different numbers that sum up to 1, and each of those numbers just represent the probability of that data point belonging to a class. And so therefore, the softmax activation function is very, very appropriate for multi-class classification problems. And then finally, for regression problems, you can use linear or ReLU activation functions. I would say linear if your values go negative, and then linear if your values go to negative, and ReLU if it doesn't. So yeah, both of them actually, if you look at the ReLU function here, if you just look at the positive numbers, it is a linear function. So again, depending on what you're trying to predict, you would use different activation functions for your output layers.
What would be a regression? Well, binary I understand, multi-class I understand, but what's regression in this case?
Oh, regression, like literally your mod 2 project. You can actually take your housing data project and you want to predict the price of a house. So you can actually feed in your data for a regression problem, and as long as
numerical in that case, like the numerical here in this case for the price of a house.
Yes, yeah, a continuous value, yeah.
Okay, continuous value, get it, makes sense.
Mm-hmm. Yep. Any other questions before we move on to the next thing? Awesome. I will say, like, getting an instinct for which activation function to use, especially in your hidden layers, I'm not even there yet. I will try different ones to see which one works better and adjust based on, whether my model is overfitting, underfitting. Actually, I mainly look out for whether it's over or underfitting, and then I choose a different activation function based on that. But these articles do walk through some of the pros and cons of each activation function in even more depth. So a good read. All right, so the next thing we're going to talk about is loss functions. And loss functions, which actually come together with optimizers, come in the compile step of the model. So you can see here, I have my loss function and my optimizer, and these are the next two things we're going to talk about. So loss functions, they're akin to cost functions that we were trying to minimize in gradient descent. So for example, when we were talking about RMSE for linear regression, Gini/entropy for different trees, loss functions are just the same kind of functions for neural networks. So again, it really depends on the problem you're trying to solve, which loss function you use. So for example, for regression problems, Keras does have mean squared error or mean absolute error as your loss function. So you just feed that in to here, and then it'll just compute your loss with your train and test set and try to optimize for that. There's also mean squared logarithmic error if your target has potential outliers, which is pretty cool. So if, for example, the housing project that y'all did, if y'all remember, it's been a while since then. If y'all remember that for that project, we had a lot of outliers on the high side, mean squared log error might be better. To be honest, I've never really used mean squared log error, but could be something that's cool to try. But for binary and multi-class classification problems, it's more straightforward. You always want to use either binary cross entropy or categorical cross entropy. How these work is basically like entropy when we were doing decision trees, but it does it for you with like binary and multi-class. So I also, again, put an article here that talks about the different loss functions, and it's mainly for like different use cases, which one would you use? And so with that, we have different optimizers because you're always trying to optimize your loss function or minimize your loss function in whatever machine learning problem you're doing. So again, some summary articles here. But different optimizers are just different methods or paths that your neural network can take to find optimal values. Experimentally, ADAM, which is derived from adaptive moment estimation, that's just what ADAM stands for, is a good one to use. So usually you can start with ADAM, and if that still doesn't work, try different things, but ADAM usually performs the best. How ADAM works, which is pretty cool, it's kind of a combination of these first two. So to first talk about RMS prop, RMS prop stands for, I think, root mean square propagation, if I'm not wrong. I think that's it. But basically, it maintains per parameter learning rates adapted based on the average of recent weight updates. So with all of these optimizers, the learning rate actually changes per parameter, which makes sense, right? Because if you have a constant learning rate of like 0.01 for all the parameters, and by parameters, I mean like even in this small neural network, I have 277 parameters. If they all have the same learning rate, that means that their weights can only be adjusted by so much every time. So it makes sense that for different parameters, you're gonna have different learning rates, just so, you know, for different changes that your neural network is seeing, you can adapt better. So RMS prop maintains this based on the average of recent weight updates. So it's only gonna change your learning rates based on, you know, the average of maybe your past 10 weight updates. And that basically means that if you have noisy data, your weights won't change so much due to that noise. So yeah, it does well on non-stationary or noisy data. There's also AdaGrad that you can try. AdaGrad does this, but it also improves performance on problems with sparse gradients. So by sparse gradients, you think about, all right, where do I have sparse data? NLP is a situation where you have a lot of sparse data. Like if you think about every document being a row and every column being an individual word, you have a lot of zeros. And with a lot of zeros, you have a lot of sparse gradients because when you input 0, it's hard to know how to adjust. So with natural language and computer vision, which we'll talk about actually right after this, AdaGrad could be something that you use instead because of all the 0 inputs. And then finally, ADAM is kind of a mixture of both. Instead of adapting parameter learning rates based on the average first moment, so the mean, it also makes use of the average of the second moments of the gradient. So it takes into account the mean and the variance of all of your parameters and adjusts learning rates based on that. So as you can tell, ADAM is taking into account more things when adjusting learning rates. And so that's why it's usually the better optimizer. But you can also play around with different ones. Cool. Any questions here?
I'm so sorry to back up, but can you go over what a learning rate is again?
Oh, yeah. So a learning rate is something that you can actually define. I'll actually, in the next thing, I guess, we'll go more into learning rate. But
okay.
But learning rate is basically, if you remember gradient descent, how much your slope will adjust with every learning step. That's the learning rate.
Okay.
Anything else? All right, so the next section is also about learning rate, but you'll see why we talk about this separately. So with learning rate, you can actually define your learning rate when you compile your model with the optimizer. So I didn't do this here because they can do it by default. But I think if I do it in the optimizer, there's a way to include a learning rate with the optimizer here. But basically, optimizers usually change up the learning rates, as we just talked about before. The learning rates are going to change with every epoch and with every like batch that you're putting in. So you're really just defining the initial learning rate, which is again why you don't have to put that there, but it's just good to know. You can actually set your learning rate beforehand. But if you do decide to set your learning rate, some things to consider. If you set it too low, training will converge, but it'll do so slowly. So imagine like a very, very low learning rate, like 0.0001. Your parameters are just going to adjust very, very slowly. You can run into, not the issue, but you can likely optimize your neural network pretty well, but it'll just take a very, very long time. If you set it to high, it might actually overshoot the optimal parameters. And then if you set it slightly too high, it might converge eventually after missing the best values. So learning rate, I usually don't play around with learning rate too much, but you can, it's an option. All right, now I think this is the last thing I'm going to talk about, regularization. So I mentioned before that overfitting is an issue of neural networks. You can imagine because there's so many parameters. If you optimize too much to your training data, you're going to run into overfitting problems. So why neural networks tend to overfit? As a neural network learns, neuron weights actually settle into their context within the network. So basically what that means is it's easier to talk about it in the context of an image. So we'll talk about it abstractly for now. But imagine in a neural network with like 500 neurons, maybe 100 neurons have been trained to recognize things like colors. Another 100 could actually be trained to recognize textures in an image, like is something like clothing or is something an animal. Another 100 neurons could focus on things like edges. Are there harsh edges? Is everything smooth like a painting? Stuff like that. So just by the nature of there being so many parameters to tune, weights of neurons start to get tuned for specific features, and they actually have this specialization. So neighboring neurons will inevitably become very reliant on specialization because, as you keep learning and over-learning a specific thing, basically what I have here, it can be taken too far and result in a fragile model too specialized to the training data. Just for some, I guess, lingo, the reliance on context for a neuron during training is referred to as complex co-adaptation. So if you ever hear that phrase, that's what's happening. So there are several ways that you can get over-regularization. So most simply, you can add L1 or L2 regularization within each hidden layer. So actually here, as an argument, I can add regularization. So you can either specify L1 or L2. And if you don't remember what that is, it's L1 is akin to lasso and L2 is akin to ridge. It just makes our penalty terms either squared or absolute value. Most of the time we use L2. Something else you can do is a dropout layer. And I'll talk about dropout layer in a little bit. But also there's a third method, which is more preferred for neural networks, especially when you don't want to overtrain, is something called early stopping. So your model doesn't overtrain. And that I'll get into a little bit more later as well. So first, let's talk about dropout. So dropout is a technique where randomly selected neurons are ignored during training. So they're dropped out randomly. So this means that their contribution to the activation of downstream neurons is temporarily removed, and then therefore their weights are not updated during backpropagation. So you can actually add dropout as a layer in your neural network. Let me see if I have an example. Oh, I guess my example I have here is just like this. So in your model, you'll just do model.add dropout. So I could, for example, put like a model.add dropout here. And so what happens is from this 12 to this 12, if I do dropout, let's say 0.5, it's going to ignore 6 of the neurons. And that just stops it from overfitting. Here I have 0.2. If it's 0.2, it'll ignore 20% of the neurons. Yeah, I forget if it rounds up or down, but Yeah. So another thing that you can do is early stopping. And what you do with early stopping is you can import this early stopping part of Keras, and you can just introduce this as a callback to your model. And then you just have to give it a patience parameter. And basically what this does is it watches your validation data. It watches your validation metric. So for example, if you're running 100 epochs and your validation goes down, if it goes down consecutively, if it goes down, for 2 epochs consecutively, it'll just stop your neural network there, saying, all right, this is the best that we have. So yeah, that's early stopping. So you don't keep training your neural network after it started to overfit. So that could be something useful to add in a neural network as well. Any questions about this?
Can you just take it to the optimizers first?
Yeah.
So now, let's say if we are splitting between our optimizers, between a part of it is Adagrad and the other part is if we are using Adam, right? Then what happens on the dropout?
Okay, so optimizers are determined when you compile your model. So the optimizer is actually for your entire neural network. So one neural network only has one optimizer.
Okay.
Yeah. So you don't have to worry about
splitting it. Okay.
Yeah. So
I thought like I mean, when I thought like we could actually
per layer, right?
Yeah, we could.
Yeah. So the only thing that is per layer is the activation function.
Okay.
I have a question too.
Yep.
Well, I was slacking with Ben Jacobson about one of the labs, and how does this relate to like the loss in accuracy? I mean, and it's linked to an article about overfitting. So how's it all kind of related?
So the optimizer is. Oh, say that again.
But anyway, also with he linked to something that I think that this early stopping too, that shows that when the training and the test data start diverging, I guess their accuracy starts diverging. That's when it stops.
Yep. So basically, if you see, let me just use this as an example, I guess. So this is the neural network that we ran last time with 300 epochs apparently. And we see here the accuracy, it's actually jumping up and down a good bit, right? Like, let's just take these last few as an example. Let's find a good sequence where it keeps going down. All right, so you see here it goes from 73, actually goes down to 72 and down to 68. And then the loss also kind of jumps. And loss, you want less loss. So you can see here the loss actually goes up a little bit. Where was I? Yeah, it goes up from 61 up to 65. So basically between step 288 to step 290, our model is getting worse. Basically, the optimizer is what is working to try and get this to go as low as possible. So the optimizer is the way gradient descent is working for every single parameter to get this overall loss to be as low as possible.
Okay.
And then early stopping is going to see that, all right, well, our model's not getting any better over these couple of steps. So let's just stop. We don't have to run 10 more epochs for no reason. Let's just stop after it goes down. If I do like patience equals to 2, let's just stop our model after it goes down 2 consecutive steps.
Okay. So and those epochs, why is there like 2? There's loss accuracy, then val loss, and val accuracy.
So this is the training data, and then this is the testing data.
So is it comparing the training and the testing data as well in those for the, or just looking at one set?
It's kind of looking at them together. So so yeah, as as you're fitting the model, it's going to look at the training data, it's going to look at the training loss and accuracy, and then of course it's going to take into account the validation or like test set with each epoch to make sure that it's also trying to account for overfitting. But yeah, it does look at both.
Okay.
Well, I guess more specifically to your question, when it's training, it's only considering the training loss and accuracy, but after each epoch, it will run your test set through just to make sure just for you to make sure that it's not starting to overfit, if that makes more sense.
But the patience, whatever, is only working on the training data.
The patience is working on the testing data.
Oh, and the testing data. Okay.
Yeah. To my knowledge. Let me just do a really quick. Keras early stopping.
On that, wouldn't it affect, you know, the model knowing or taking a look at the testing data? Wouldn't that cause leakage?
Yeah. So that's why when you're training your model, so imagine, so you can sort of think of this as like at every epoch, you fit your model, but you're just testing it on the side. So when you're training the model, it's not going to take into account this information. The validation information is not taken into account with each epoch as it's adjusting.
Okay, so it's sort of like it's running it, and then after it runs it, it's like, let me see.
Yeah, that's right. But the model doesn't change itself based on the validation data.
Okay, that makes sense.
Okay, good. So with early stopping, I believe that, I want to say that it is.
It just says with no improvement, though. It doesn't say where the improvement is looking, where it's looking for that.
Yeah, I honestly have always, oh yeah, it monitors, oh, I guess you can tell it which one. So this one's monitoring validation loss. I guess you could have it look at loss.
Okay.
Yeah, so I guess based on this, you can monitor the regular loss, but you can also monitor the validation loss. Cool, yeah, I actually didn't know that either. All right, any other questions? Cool, so after this, we're actually gonna now talk about how you can use neural networks for images. One thing that I want to reiterate is that you can technically not use convolutional layers, and basically convolutional layers are a different kind of layer. We can actually see that in my .add, I have these new kinds of layers, whereas previously we were adding just dense layers. So you can actually do your image classification project without convolutional layers, but I do think you'll get much better results, and also it'll be a better use of your time if you introduce convolutional layers for your neural network project. So that's why I wanted to talk about it. All right, and I think one of the labs actually does image classification with dense layers. I think to see the convolutional layers in the labs, you have to go to the appendix, just so you all know. All right, so let's talk about convolutional layers. Any neural network with convolutional layers is called a convolutional neural network. CNNs for short are mainly used for image recognition or classification. They can be used for video analysis, NLP as well, although not as likely, as well as speech recognition. You can also use convolutional layers for analyzing waveforms. That's actually a cool application I've seen of it, but most commonly used for images. So before we get into using convolutional layers, let's get into a bit of like the theory and the motivation behind using convolutions. So before we talk about convolutions, we have to think about how do our brains versus computers see an image. So the way our brains process images, again, I am no like biologist, but I'm sure some of you have seen like images like this where it's kind of ambiguous or it kind of like trips you up, where this could either be a muffin or a dog. But for us, we might see, all right, there's a tail, there's like a wet nose, flappy ears, good boy, and conclude that we're seeing a dog. There's not one singular thing about a dog that our brain recognizes to be a dog, but more so an amalgamation of different patterns that allow us to make a probable guess, right? Like I do get confused by some of these muffin images. But we think about how computers see images. They see it as numbers. They see it as tensors or as matrices. So to computers, every color image is a 3D object or a tensor. So it's composed of 3 matrices, one for each primary color that can be combined in varying intensities to create different colors. So if anyone is familiar with color theory, I'm not super familiar, but every color can be made up of some intensity of blue, green, and red. So basically, these are stacked on top of each other, and then combined, you have your image. If it's a black and white image, you only have one of these matrices, and it just describes the intensity of like the black. So it's like grayscale.
That's the reason we have the RGB patterns.
That's right. Yeah, that's exactly right. All right. So with images, they are actually all they're actually all numbers between 0 and 255, which again indicates the intensity of the corresponding primary color in that pixel. So that brings us next to the idea of convolutions. So to convolve means to roll together. Basically, how convolutional layers work is they make use of linear algebra to identify patterns using pixel values. And how they do that is they're actually taking a small matrix, and this is actually a pretty good diagram, I think, is using this small matrix and moving it across an image and then multiplying the numbers together every time it moves. And so this is a way it sort of detects patterns. So more terminology, this mini matrix that's being moved across is called a kernel or a filter. And basically what's happening here, you see on this small matrix, there are numbers, like on the top, you have -1, -2, -1, and then +1, 2, 1 on the bottom. What it's doing is for every square of 9, it's going to multiply the corresponding image of whatever it's projected on. So if it's on this top part, it's going to take like 0 multiplied by -1, 0 multiplied by -2, 1 multiplied by -1, all zeros across this, 1, 2, 1. And then that's what these numbers are.
One quick question. So will it take sequentially? The top layer only talks to the top, and then the middle one.
Yeah. So as you can see here, it'll usually, I believe, the order actually does scan across an image from left to right, top to bottom. And it does correspond, like wherever the 9 grid is, it's only being multiplied by the number that's overlapping it, if that makes sense. And then, it is going to like move across the image. Something that you can actually define, and I think I talk about that later. You can actually define how many steps across the image it moves, and also how big this filter is.
So what happens like when an image is highly pixelated, or maybe like the image which is got which is a very large image, and then like it's got like a lot of pixels attached to it?
Yeah. So, well, if an image is very pixelated, it just means it has very few pixels. And I mean, this process will just be faster. Whether it's able to detect anything, again, it depends on like the resolution. It depends on like, how big the object is in relation to the pixels. So smaller image, this will run faster. Larger images, this will take longer.
Same way for the resolution? I mean, higher resolution, more time.
Yeah.
Okay.
So in that GIF or GIF, whatever you say, wait. So is it it seems like it's taking 6 numbers and ending up with 1 number.
It's taking it's taking 9 numbers and ending up with none numbers.
9 numbers.
No, 9 numbers and ending up with 1. So yeah, you're right. They're multiplying all, and then this number that results is the sum of the multiplied numbers.
The sum, okay.
Yeah, I actually I didn't mention that earlier, so thanks for clarifying. So basically, as you can see here, with numbers like this, on this filter, different arrangements of numbers on this filter help to identify different kinds of patterns. So there's a lot of theory that goes behind this, but basically something that has like zeros on its horizontal axis are good for identifying, I think, horizontal edges in an image. So yeah, that's pretty cool. So yeah.
One quick question about the filter on this.
Yes.
Is the filter always going to be, -1, -2, 1, or is that something that we decide?
Yeah, that's a good question. So we don't get to decide the filter numbers. the filter numbers actually change during your training process, and it changes during the backpropagation process. So with backpropagation, it'll figure out what filter do I need in order to try and optimize my result. Yeah, so actually I think I have in this next line here. So yeah, when a filter is rolled over, first the resulting matrix is called a feature map. So this blue is actually called a filter map. Literally a map of where each pattern of the feature is in the image. And elements with higher values indicate the presence of a pattern the filter is looking for. And then, yeah, the values or weights of the filter are adjusted during backpropagation. So yeah, you don't have to worry about, all right, I want to look for edges, so I got to make sure that my filter looks like this. You'll see later in the code, we don't have to worry about any of the filter values.
All right, awesome.
Anything else? All right, now there are also some things to think about when defining your convolutional layers, and two of the main things that you decide on are padding and stride. And sorry, I think this is pretty small, so let me zoom in. So padding and stride. With padding, sometimes it's convenient to pad the input volume with zeros around the border, helps with detecting patterns at the edge of an image. Padding is literally what's happening here. Basically, if you, okay, ignore these ones on the side, but imagine I have this filter here, basically having a padding of zeros around the border will allow like the middle of this filter to reach the edge of the image. So just make sure that you're not missing anything on the edge. So you can add a padding as a hyperparameter in your convolutional layer. Another thing that you can edit, that you can tune is the stride. And the stride is the number of pixels to shift the filter on each roll. So it's literally, this is a stride of 1 because it's moving 1 pixel right and 1 pixel down. So you can see it as it's going through one row, it only moves 1 pixel at a time. And then every time it shifts downwards, it only shifts down by 1 pixel. So sometimes if you have like a filter of like 5 by 5, it might take a long time to, you know, shift it across the whole image, and you might not need that level of, I guess, intricacy. So you can actually set the stride to be equal to 2, and then so it will go 2 pixels every time, just in an example. The larger the stride, the smaller the feature map will be, but we will lose more information. So it'll end up being, I think, a little bit more efficient, but again, you know, if we have a stride of like 3, for example, in this case, it's only going to do this 9 and then go immediately to, I guess, this 9 because it can't move 3 all the way. But yeah. Any questions before we move on to the next kind of layer, and then we'll get into building a convolutional neural net.
Yeah. So one quick question. So what we do is, while we are working on images, we'll say that, okay, this is one example image of, let's say, a dog, right? And first it will scan and it will create the RGB format or the grid, the third one with the third grid. And based on that grid, it will scan the other images when we upload, and we'll say that, okay, check this image whether this is dog or not, correct?
That's one way you can go about it, but typically if you're classifying, you would feed in a lot of dog images for it to really recognize all the different kinds of dogs. And with classification, you usually have like 2 classes, right? So usually if you want to train something to recognize a dog, you would give it, let's say, 1,000 pictures of dogs, and then 1,000 pictures of just not dogs, anything that isn't a dog. And then your machine will learn, all right, which are the pictures that have a dog in it, which ones don't, based on, you know, all of these. And maybe it'll detect like fur patterns, maybe it'll detect like general shapes. And then that will basically teach your neural network to detect dogs.
So the face recognition app, which is there, it has been just feeded with, like, let's say, millions of images, and now it's able to recognize the pattern.
Yeah, that's one way to do it. If you have a lot of, like, I know that there's one that's like, you upload your image and you see like what celebrity you look like. In that case, it's slightly different. In that case, you're feeding in images. And then when you feed in images, it's actually gonna compute similarity of images. And then it'll just give you the, it'll just return you the image that has the highest similarity. That's a completely different kind of neural network, so I don't want to talk about it too much. But the whole idea of that is instead of trying to use our neural network to make a prediction, you can actually have your output layer be not an output layer. So you can have your output layer literally be another dense layer. And that just means that your output will be like a 12 value vector. And then you can just compute similarity between different 12 value vectors. If that doesn't make sense, it's okay. You don't have to worry about any of this concept for your projects. But that's how you would do it.
What will be the project for this?
Yeah, for this mod project, it is an image classification project. It's black and white images, so you don't have to worry about it'll be faster because it's only black and white images. And it is, I believe, detecting pneumonia in chest x-rays.
Okay, so we'll feed in, right, all the X-ray images, and
Yep.
based on that, it will have to tell that whether that particular scan image has pneumonia or not.
That's right. That's right. I actually have an example of like a CNN classifier right after this, so we can sort of see how that would work.
Basically, like when your chest X-ray is there, like when it is filled with water, the lungs, right, it reflects a particular.
Yeah.
And that's how maybe it is detecting.
That's right. Yeah.
Okay.
Anything else? All right. Okay, so there's actually one more kind of layer, actually two more kinds of layers before we get into building a convolutional neural network. So after convolutional layers, which are these, usually it comes with what's called a pooling layer. And you can sort of think of pooling layer as like an aggregation layer. It just helps with the computational power of your neural network. So after convolutional layer, your feature maps, which is basically after convolutional layer, you see a pooling layer. That's what's happening. Your feature maps will be fed into a max pool layer. And this max pool layer, I'll get into that later. But basically, like convolutions, this method is applied one patch at a time. So you again have like smaller feature maps. And then max pooling just takes the largest value from one patch of an image and then places it in a new matrix next to max values from other patches. So basically, this is the result of this. So this, for example, is your feature map. And a pooling layer will aggregate that another layer. So basically what's happening here, if I have a pool with 2x2 filters and stride of 2, each filter will go over a 2x2 here. So this is one, this is one, this is one, this is one. And you're just going to take the maximum value there. And then getting the maximum value through a pooling layer, you end up with this. And so this results in a new feature map. So it goes from this to this with a reduced dimensionality that is then passed into another convolution layer usually to continue the pattern finding process. So this is usually repeated until you're passed to a fully connected layer that proceeds to classify the image. And I'll talk about that next. But this pooling layer just, again, helps with aggregating. And in some way, it puts information together. Yeah, that's how I understand it. Any questions on this? I'll just say that usually if you have a convolutional layer, pooling layer comes after it, although it's not always necessary. Okay, so convolutional and pooling layers, as we've seen, they're all 2D, right? And getting from 2D, if we want to make some sort of prediction, and our predictions are one-dimensional, so we need to somehow get our data to be one-dimensional, and how we do that is through a flattening layer. So every convolutional neural network that you're trying to make a prediction with has a flattened layer. And we'll actually see an example in a little bit. But you have this flattened layer that just takes a 2D matrix and just strings it out into a 1D vector. All it does is it starts with the first row and just strings the next row and next row onwards to just get a 1D vector. Just so it can be passed into a normal, densely connected layer for classification. And then using this vector, you can just plug it into an output layer with any appropriate activation function. So if your problem is multi-class, you'll put it in softmax. If it's binary, you'll give it to a sigmoid. But yeah, we'll all see that in this CNN example. But before I get into this, any other questions? All right, I'm gonna run these real quick so that we can see this.
I have a quick question. I see you're importing sequential. I saw in our lab. What is that again? Sequential?
Yeah. So sequential. All the models that we use in this course are sequential models, and it just means that your layers come one at a time. So there are some models that your layers want to talk to prior layers.
Okay.
They're just different kinds of neural networks, but sequential just means that your data is fed through one layer at a time.
Okay.
That's a good clarifying question. Anything else? All right, so with this, I'm actually going to use one of the Keras built-in data sets just because it's easy to use. Yeah, this is the data set. But everything else I think we've talked about before. With images, we can actually plot them. This is actually matplotlib. You can actually plot images. There's a image show that you can actually showcase your images. So these are just some sample images from this data set. I think this is there are 10 different classes here. There's like animals, there's trucks, cars, boats. It's a pretty random data set, but I'm just using this as an example. I will say for image classification projects, there's not too much EDA you can do aside from see some examples of images and for example, your class balances, but I'll go through all of that on Thursday when we talk about the project. So just really quickly, let's just look at the class balance. This is a very, very balanced data set, so we are good. This is what our model looks like. So several things to point out. Structurally, not structurally, syntax-wise, exactly the same as what we were dealing with before. We start with a sequential model. And then we're just going to add layers to it. But instead of adding dense layers like we did last time, so previously we just added 2 dense layers, we're going to add a bunch of convolutional layers and pooling layers. So here you can see I have 2 sets of convolutional and pooling layers. The numbers, first I want to point out the input shape here, where previously we gave it an input dimension of 8 because this had 8 columns. Here we're giving the shape of each image. Now, each image is a tensor that is 32 by 32 by 3. And this you can actually find from here. So you know that each image is only 32 by 32 pixels. So therefore, they look very, very pixelated. But you can sort of make out what they are. So you have to give it that. And then within each layer, this is what's going on. So here, 64 is the number of nodes. And this 3 by 3 is just saying that we're using a 3 by 3 filter in this convolutional area, in this convolutional layer. And this 2 by 2 just means that we're pooling 2 by 2. And then same thing here. And it goes from 64 to 32 just to demonstrate the funnel effect, where usually you're reducing the number of nodes as you go through your layers. After these 4 2D layers, oh, yes.
Yes, I just want to have a clarification on the image size. So
Yeah.
all the images that we upload have to be on the same size, or right when the scanning happens, it has to be like it can be different sizes because
they all have to be the same size. So even
first,
if they're not, oh, go ahead.
So first, like we have to convert every image to the same size and then put it for scanning. I mean,
yes, but there is a built-in function to do that for you. I don't have it in this notebook, but if you look at any of the image classification notebooks in your labs, they actually have a line of code that it'll pass any image file you have and it'll coerce it to a certain size. It'll force it to be a certain size. Yeah, because your inputs all have to be of the same size for your neural network. Yeah, you guys will see it's called the image data generator, where it'll read like all the images from your computer and it'll coerce them to be all the same size? That's actually a really good question. So yeah, that's what you have to feed in here, your input shape. Where was I? Oh yeah, after all of these 2D layers, you can see here, I just have a flattening layer to make it into a one-dimensional layer. And then I pass it through another dense layer, and then the final classification layer. So what I'm doing here, my loss function, I'm using categorical cross entropy because I have 10 classes here. I am using the SGD optimizer just because it's different from the atom optimizer. And I'm going to test for accuracy. So if I compile this, and hopefully this won't take too long to run. I think the last time this didn't take too long. But yeah, you can see that because it's an image, again, it's doing all of those mappings. So it's going to take a little bit of time. But this stuff is the same. We're fitting our X train and Y train data. The only difference being our X train and Y train data has these shapes. Our Y chain looks like this. And then we are also feeding in our test data the same way. Yeah, this is only going to run for 5 epochs, so it's still going to take some time, but not forever. And yeah, since I already have some results printed out here, we can just take a look at the results. This is not going to do very well because it's only 5 epochs, but you can see here that it's not doing well with 5 epochs. So yeah, not a good model. From the students that have just done their image classification projects, they trained each model for at least, I would say at least an hour, and we don't have time for that. So basically, if I want to make this better, I will literally increase the number of epochs to like maybe 100. Which, as you can see, this is going to take a while because right now, I think the accuracy is great. It's only at 10%.
If you use that Google the Google, would that make it faster because they have more computers behind them?
Yes. Well, it depends on your computer. So it depends on if your computer is faster than whatever technology they are using. So for example, here, they're using like, I think a GPU. I personally don't know too much about like processing power, but I know that my computer, because this is Flatiron School's computer, it actually runs at the same, it has like a very, very similar computational power as the, okay, so you can do that here. It has something similar to like the GPU here. You could try the TPU, which might be faster. But yeah, I think for most computers, this GPU option will help it run faster. One perk of using this as well is you can actually do 2 neural networks at a time. You can run one on Colab, one on your local computer. That's what a lot of students do.
Okay.
Yeah. Cool. Let me just check and see if there's anything else. Yeah, this is the this is my example with only 5 epochs, but there is actually a walkthrough for this data set on this link, and you can see they actually managed to make predictions. So feel free to look through that, but you would set this up the same way. I think in their final example, they ended up with like 10 plus layers. So feel free to look through that if you're curious to see how, how a neural network is able to detect all of these different images. But yeah, these will save for next Tuesday, because next study group, I did want to talk about our project. If there is time, I will talk through some of this stuff on Thursday as well. But yeah, we're just about at time. Does anyone have any questions to close out?
So the GPU, I know it is graphics processing unit, which is like where you do it. And what will be
the other one?
The other one, TPU. What was that?
Yeah, the other one is TPU. What does TPU stand for? Let's see. Tensor Processing Unit.
Okay.
Yeah,
so
it was actually
specific to only Google, or every system has it? I mean,
it was created by Google. I know that companies make TPU processors. I'm not familiar with that area though.
Because most of the, I mean, as far as I know, the laptops and all, right, usually do not have TPUs.
Yeah.
Unless
Yeah.
gaming laptops, I don't know about it, but
I honestly don't know either. I don't know hardware, unfortunately. But yeah, could be something to look into. I will say, like, for the neural networks that we're running for this course, you probably don't have to think about this stuff, honestly, unless you really want to get into like neural networks in the future. You probably don't have to worry about this.
yeah, actually the what do you say? The X-ray images put me interested.
It is very, very interesting. I know, but just not to like caution, I guess to caution you all who are thinking of doing that project. It is a lot of waiting. Even yeah, the students who just did it, my other class just did their projects a couple of weeks ago. They were waiting a lot for their models to run, and it does take up your entire computer's processing power pretty much. So I mean, on one hand, if you want to take a lot of breaks, that could be one to do. You just have to run your model and you can walk away for 2 hours. If you want to set up grid search with that, which I'll talk about next time, that could be an overnight process. I had one student run from this last class as well. He ran like a grid search for 17 hours on his computer. So that's like the kind of waiting that you're thinking about, not like the 20-second wait, but like hours of waiting.
So the arrow which was moving, it was right while you are running the epochs. This it's automated, or you have to have some kind of widgets
Yeah.
activate.
So this is the default. You can actually edit this in the number of the verbose. So I think I have it here. So if I have verbose equals to 2, it's going to print out all. I think if I do verbose equals to 0, it's not going to print out a single, or it might print out like every few. That's something that you can actually also edit. I forget off the top of my head where, but you can put a line somewhere to say, only tell me the result every like 10 epochs, for example.
Okay.
Anything else? All right. Well, on Thursday, remember, I'm going to talk about the project. I'm going to send out a document as usual with all of the guidelines for the project. So look out for that. And then Monday is a holiday. I'll post something in Slack about that as well. So our study group will be pushed to Tuesday next week. All right, then if there's nothing else, please Slack me if you have any questions. Again, I mentioned if you want to start working on your project, I'll actually send out the guideline right after this so that you can take a look at that first. But yeah, I will be going through that whole document on Thursday. But feel free to get started if you'd like. If anyone has any questions about deciding which project you want to do, I know actually some of you have already told me. But if you have questions about which project you want to do, feel free to let me know as well. All right, then I will see you all back here on Thursday. Have a good rest of your night, everybody.
Oh, yes,
Bye.
thank you.
Bye.